Hello everyone. So I'm Sagnik, and we're going to present the FA2023 right now. So glad you all can make it. So a couple of announcements. We have started a lockpicking support group, and you could come down here with us to practice lockpicking every Mondays from 8 to 9 p.m.
I want lockpicking chill with you.
Hooray! Yep, lockpick and chill. So there's the meeting flag and mandatory XKCD. Yeah. Also, yeah, we don't paste your private key. There's a good reason why it's private. Yeah, it's moving. So, we got it. Okay. So for the first section, we're going to go over the Chinese Remainder Theorem, which is a big part of like what we'll make up for some of the upcoming sections. So remember modular arithmetic from last time? Well, it gets even more intense now. So arithmetic mod n means we work in a closed circle with respect to the modulus of n. So we are able to like cycle integers every time we process, essentially. They're just straight up turn. Okay, so since we are looking at values mod n for some n, we lose information because we only restrict ourselves to like a small circle of specific integers, specifically the ones from 0 up to n. So every time we keep cycling like through those, we lose information about like what the original number was. It could be a lot of things. Suppose I asked you to find what 4 times 4 mod 3 was, right? That's 16 mod 3, the remainder would be 1. So you know that the result there is 1. However, what if I asked you to find what x divided by 4? Well, 4 does not really divide 1 that comfortably, does not divide 3 that comfortably. It'd be a lot harder to find in general because we can't really like reduce it to some integer mod from another integer. There's a lot of values we could take on, and it's just a pain. Now, suppose you know 4 times 4 mod 20, which is 16, as you just do the multiplication. However, what if I told you to divide it by 4? Our modulus is going to divide by 4, 16 is going to divide by 4. It's a lot easier this way as well. So can we use this to our advantage is the big question. And the answer is yes, we can. So in the 3rd century, Sunji Xuan, I'm going to very much butcher this guy's name. Sunji Xuanjing first created an ancient Chinese text that depicted the Chinese Remainder Theorem. And the original problem was, let's find some x such that x is between 0 and 105. 105 was like the original number. And we can divide 105 by these 3 prime factors. And the main thing to note is that they are all co-prime to each other, so they don't intersect. So we basically have a system of modular equations. The Chinese Remainder Theorem tells us that there is a unique x, in this case 23, such that that's equal to, that's going to solve all 3 of these equations simultaneously, mod 3 times 5 times 7, which is 105. And of course, 105 is a very general thing. Anytime really you have like co-prime integers as your moduli, such as in this case primes p1 up to pk, you are able to find a unique solution to this system of mod equations. So we have a unique solution for x mod p1, p2, all the way up to pk. Does anyone have any questions? Okay. So why do we exactly care? This means that any cryptographic system really can be solved using modular arithmetic. So any modern cryptographic system has to be careful with the primes used because you could easily devolve into the space where you just have to solve a lot of modular systems. So for example, we define a prime p such that p minus 1 has a lot of small factors. We call that a smooth prime. So we can use Foley-Hellman from last time to attack this prime. And the Chinese Remainder Theorem and Foley-Hellman was used to do an attack on TLS and SSL by an attack called Logjam in 2015. Now, we're obviously able to do these in a lot easier way through SageMath, because SageMath, like Python, but has a lot of built-in libraries to support math operations. And CRT is one of them. If I recall correctly, the way you do it is you pass through like some CRT function. You have an array of like the left side of the mods and then the modules themselves. So it's also very easy to use for like large systems. So one core object in these modular systems are what we call a generator in the discrete log problem. And for now, all you need to really think about for generators are that they essentially are able to divide every possible non-zero remainder 1 to up to p minus 1 via their powers. So g to the 0 will correspond to one value in this set. G to the 1 will correspond to another up to g p minus 1. And all powers of g will essentially convert into that set. And we define p minus 1 to be the smallest value such that g to the p minus 1 is congruent to mod p. For now, you can just take a step back. If you want to read a little more into this, I would suggest looking at Fermat's theorem, which is the more general-ish case of this fact. But the point is every number mod p can be written as a part of g, making this arithmetic easy because we can enumerate as a value. There's one more questions on that. That's quite a lot. Yep.
Just what kind of properties does the number you have to have for this feature?
The thing about G is that if we have G anyway solve this, then this thing will be true. We just need to have the powers of G mapped to any value. It's not necessarily, well, G to the power of 0 will obviously map to 1, but you could have G1 mapped to p minus 1. You could have G1 mapped to like p minus 3. As long as you're able to prove that like for every power of G from 0 to p minus 1 specifically can be mapped to the set, then the property satisfies and it becomes a generator. A lot of primes have like a list of generators. The more formal term in math would be primitive. Yeah. But it doesn't really have to be in like a single order from 1 to p minus 1 specifically. Any G power except for 0 can map to like the rest of the set. So as long as it does that, you satisfy. All right, so something in action for CRT would be if we were to find A such that G to the power of A is congruent to capital A mod P, where P minus 1 can be broken up into its prime factorization. And let's let Ri equal to P minus 1 over Pi to the Ni, Gi equal to G to the power of Ri, and Ai being A to the power of Ri. The reason why we divide it by some element in that will be clear. So let's say we have to solve the discrete log for Gi to the power of A. This is easier because every single number here is some power of G to the R1, because we define G to be some generator from the previous slide. So Ri divides P minus 1 because we specifically define Ri to be P minus 1 divided by some element in that prime factorization. So since Ri divides P minus 1, there are fewer values of AI such that Gi to the AI is 1 mod P. So we have a smaller and tighter cycle. So there are less AI to try because our search space is now reduced, and therefore it's easier to find because we only have to cycle through a smaller search space. So CRT tells us that X has a unique solution. X is congruent to Xi mod Pi to the Ni via what CRT states, that there is a unique solution to the system of equations. And the system of equations in particular is all of the Xi mod each factor in the prime factorization system. Any questions? That's kind of a lot. So, okay. So that brings us to elliptic curve Diffie-Hellman. So the whole point of the last slide was that traditional Diffie-Hellman was a lot less secure because of the Chinese Remainder Theorem. So to rehash what the normal DH from last week was, we took A from the set P2 to P minus 2 and B from 2 to P minus 2 with the values taken from like a uniform random sample. And we found G to the A mod P, which was Alice's public number. And we exchanged those public numbers to get the shared secret. So that's the DH we know from last week. Now, the better version of this would be the ECDH algorithm, which is where we have to use plain numbers or even just plain modular arithmetic to find more complex values for this. So modern security picks these values via a new tool called elliptic curves. And these curves are of the form y squared equals x cubed plus ax plus b, where we can really pick any a or b to represent this. So the name comes from when mathematicians were trying to figure out like the general formula for the arc length of an ellipse, and they stumbled across this equation while they were going out about it. So normally they're of this form right here. So as you can see, they kind of vary wildly from like a very nice uniform curve to maybe a small little circular object followed by a hill on the side. And it kind of looks like a droplet forming in a lava. Kind of what I like to talk about. So a lot of different curves. But the main thing to know is that you could actually perform some form of addition or multiplication on this curve, such as if you're able to take P and Q and you wanted to add them together along this curve, you'd put a tangent line through, well, a secant line through P and Q, and wherever it touches the value on that curve, you'd project it downward across. So that would be equal to P plus Q. And over on the left side, if you wanted to do 2 times P, that's where you take the tangent line to the curve at P, find out where it intersects the second time, and project that down to get 2 times. So you're able to do multiplication and addition on elliptic curves that work by points. So we also have neutral elements, which are like all the way out to infinity that don't intersect the curve. And the important thing to note is that that plus whatever P you have, like infinity, would never touch the curve in the first place. So infinity plus any point would always be a neutral because it never intersects the curve. And you're also able to find inverses really easily because if you find like a point on that curve, you can simply project it downward. So these are the 4 main properties of elliptic curves. Now, obviously, this does not seem like a good idea at first because our curve is really well defined. If we have 1 point P and we already have like a solution of Q, we can simply draw the tangent line through the real solution to recover whatever lost information. So there's a clear-cut pattern in the real space. So therefore, real numbers are bad. But discrete numbers, when you take mod P, suddenly it becomes a whole bunch of nonsense. I mean, what the hell is this? There's a lot of points in space, and we're not able to really take back whatever we have and be able to like find what the missing summation is or whatever missing information, because it's just a whole jumble. And we only took mod of a relatively small prime number. In practice, you'd only pick a way larger number than 80, and you'll see the curve get like really messed up for those primes. So the normal discrete log problem, you just give like some generator G, some large A, and some prime P, such that G to the power of A is A mod P. So that's the normal discrete log problem. Now for the elliptic curve, if you get like a big generator point G, A, and some prime P, you have to find A such that A is equal to little a times B over all the points multiplied. So you basically do a lot of repeated multiplications. So the reason why this is hard is because it's very easy to find or like generate the large A because all you have to do is multiplication on that elliptic curve. However, this is bad. This is really easy to do because for like a pool table, a good analogy would be if you already knew which pocket you wanted to place an 8-ball with, theoretically you would always know where it goes as long as you know like a few things, like the distance from the ball, the angle, and like the speed which you can have, right? So there's only a few points of information you need to know to exactly pinpoint where the ball is going. However, what if I asked you to find which position or which angle you hit from to arrive at this snapshot? It's a lot harder because now you need to know a lot more small unknowns and a lot more other things to be able to get to this exact same snapshot. So like that, in elliptic curve, it's a lot harder to reverse the process. So it's a computationally hard problem when you get the result of the multiplication, and you have to figure out what the exponent, or like the amount you have to multiply by once to get.
So if the security of elliptic curves is still predicated on discrete log, why use elliptic curves versus just normal discrete log?
Well, because some elliptic curves have like a different set of random noise that makes it a little harder to like, because now you have like another problem. You have to like figure out the structure of the elliptic curve. Whereas with the discrete log problem, all you had was a very small set of information you need to know about, like the G, A, and P. And if those three were not already like good enough, you really can't reverse the process. But even if you use the same ones for an elliptic curve, you need to know the structure of the elliptic curve now to be able to like reverse it. So there's just a general higher amount of people. And the other thing is that elliptic curves also are a little faster because all you need to do is think about like instead of something like repeated exponentiation. So it's also easier to implement for like, hardware systems. So this is kind of a rehash of what Diffie-Hellman was from a few slides ago. And the elliptic curve Diffie-Hellman is mostly the same thing, except instead now we just focus on multiplication within that space. And since we're able to do doubling really well and addition really well, we can kind of compute big A really fast. And all we need to do to get the shared secret is very similar to multiplication. And this is obviously all done over the elliptic curve over y squared equals xt plus a prime x plus b. So it's more or less the same, except now you just focus on. So that's kind of it for Diffie-Hellman. We're going to move on to RSA now. So XOR and Diffie-Hellman were symmetric encryptions because we had one key to deal with all of that. But now what happens if we introduce a system of two keys? This is asymmetric encryption. So rather than using like a shared secret key such that like that's the one key that's been going between them, we now introduce a second key such that anyone can use this to encrypt the message, but only we can decrypt the message because we have the other key. So the two keys are the public key and the private key in this case, and we use that to implement RSA. So how RSA is implemented? Well, we come to the Toshin and Euler's theorem. So we call Toshin of n Euler's Toshin function. And Toshin of n describes the number of numbers greater than or equal to 0 that share no factors with them. We say this is the number of integers that are cotimes them. So Euler's theorem says if a and n share no factors, then a to the power of Toshin of n is equal to 1 mod n. So we're able to cycle back to 1 every time we take some power of a to the power of Toshin. So that's the Euler's theorem. This theorem is the main basis for the RSA crypto system. Now, the hard problem in RSA is that multiplication is extremely easy, but factoring is a hard problem. So if P and Q are like some very large primes, let's say 1024-bit primes, then if we're able to compute n equals P times Q, then Toshin of n is equal to P minus 1 times Q minus 1. Now, it's very easy to compute n because all you have to do once you get the two primes are multiply them together. But reversing it is way harder because in order to find Toshin of n, we need to know what P and Q are. And factoring out Toshin of n is a hard problem because prime factorization is a problem that takes a lot of computation. And we need to know what P and Q are in order to get P of n because honestly, any other functions can or multiplications of even numbers can lead to P of n, but not P and Q specifically. So we need to know what P and Q are to get back to Toshin. So it's computationally hard. So let E be some public exponent such that usually NIST does 2 to the power of 16 plus 1 because it's a sufficiently large exponent and it's also easy to compute because it's close to a power of 2. Very, very large exponents are bad for reasons we'll explain a little later towards the end. And very small ones are also bad because they do stuff with them too quickly. So Alice generates some very large primes P and Q and calculates n equals P times Q, which is something we can share in public because n will already be an extremely large number, and in order to get back P and Q, we'll need the factor, which, as you will recall, is a hard problem. So she releases it as a public key, and then they calculate Toshin event, which is P minus 1 times Q minus 1 as some sort of private. This is information that's not shared publicly. So if you know E of n, you can compute D such that E times D is equivalent to 1 mod Toshin. So this is finding the multiplicative inverse with respect to mod Toshin of n. And if you know Toshin of n, then this is a fast thing to do by using the extended utility anomaly, which is, you can see from this one. So Bob will compute the ciphertext, which is n to the power of e, and will send that to Alice. So Alice can compute c to the power of d, which is congruent to m mod n, because c to the power of d would be m to the power of e times d. And as we know from Taylor's function, e times d would be 1 mod Toshin of n. So going more onto the correctness of this, if we have A is congruent to B mod n, that means that A is equal to B plus Kn. So for some K, so it only differs by like some factor of n. So ED is congruent to 1 mod Toshin of n. So you basically have ED is equal to 1 plus K times Toshin of n for some K. And if we take the powers of this, we have m is congruent to c to the power of d is congruent to m to the power of e to the power of d, which is m to the power of ed, which is m to the power of 1 plus k Toshin of n. And we can represent this as m times m to the power of Toshin of n to the k. But by Euler's theorem, m to the power of Toshin of n would just go back to 1. So we end up multiplying n by a bunch of 1s, and we can get the original message from that. So all Bob needs to really do is compute c to the power of t. And small primes are going to be very easy to enforce because at that point you could just do a lot of like the common like factoring algorithms we know, and they would be able to find them. But once you get the smooth primes, then we're able to use the Chinese Remainder Theorem because we can divide the smooth primes into some prime factorization from the CRT slides from before, and we can compute the shared secret with them. Large n or small phi of n will lead us to Weir's attack, which is another problem with using a big exponent. Because if your exponent is a little too big, you might end up having like a very small b, from which you can be using this attack to reverse. So with oracles, you can get your pen and paper out and end up doing the algebra if you're able to like get like some oracle which provides you like yes or no or some more information. So there's another fun slide about ducks that you can see, but the general solution is that like if you have some parts of a private key, you could search up through pastebin for some odd reason. You probably don't want to use pastebin to store your private RSA keys. It's not that secure, and Google is also a really good resource to be able to use some of these. So we come to the triangle of encryption, and that's that it's basically a classic pick two problem. If you're able to pick like a more emphasis on security versus some emphasis on performance, you're going to end up having a really bad cost because you neglected that. So you could kind of analyze a lot of these problems by like thinking, how hard are they going at security? Is there like some sort of weakness that they're overlooking because they went too hard on 2 of these things? So classic pick two problem. And yeah, cryptography really touches a lot of other fields like related to it, such as like data authentication, hash functions, stuff, and problems in like confidentiality, which leads to block ciphers and stream ciphers, which I might do a meeting of in the future. But so there's a lot of interconnected fields. So a few of the next meetings, we're going to be starting our own unit, yay, with Sam, and we're going to also go with Kevin for phone group. So Get ready. Start schedule.